Hey, Math Moment Makers. In this video, we can't wait to dive into another sneak peek, this time with a group of educators that I was leading a workshop with, and actually Jon Orr was there as well, co-facilitating a workshop where we were doing some exploring of a pretty complex concept, and a concept that we tend to teach very procedurally, or at least that's the way I was taught and the way I taught for many years, so maybe you can relate. What concept is it? Well, stick around and you will see very, very quickly. All right, Math Moment Makers. So what concept is it that I'm talking about? One that we tend to teach conceptually. Well, right now, as I'm recording this, it is March 14th. It is Pi Day. And anything to do with measurement and circles tends to be taught very procedurally. So for example, when we're working with circles, we tend to tell students about the relationship between the circumference and the diameter, this relationship that we call pi, that the circumference is 3 and a bit times as long as the diameter. And we tend to do this very procedurally by simply defining it for students, telling them. We might even have them explore it a little bit, but then we quickly move into algorithms. We quickly move into formulas. And actually recently, if you were hanging out with us and you checked out some of our new posts on makemathmoments.com, you would have seen that recently we did some learning around how to teach circumference of a circle. Right over here, this video here brought us into using a problem-based task in order to help students better understand where pi comes from. And the task that we used is actually called tile circle. It looks just like this. We give you a prompt where basically students notice and wonder, and then we ask them about how many square tiles do they think it takes to wrap this circle. And we let them estimate. We do all kinds of great things to emerge this idea of pi. We dove into that. We did a classroom sneak peek with that particular portion of the lesson. However, it doesn't stop there. It doesn't stop at just exploring pi. We also have some extensions to this task where we go deeper into area. And that's what we're going to be doing here and what we're going to be exploring with this group of educators through a webinar we did recently, where we gave them the same prompt, except this time we asked them how many tile circles, or tile squares I should say, would it take to fill this particular circle. That was the extension that we did, and we gave them an opportunity to explore and to try to reason through without accessing an algorithm or a formula. Again, trying to estimate in order to try to come up with at least something that's more precise than just a random guess, but without leaning on a formula that we don't necessarily understand. So the idea here through this problem-based lesson was to emerge the idea of the area formula for a circle, but through conceptual understanding. So go ahead, dive in, have a look here, have a peek, and do us a favor, hit that like, subscribe, and notification button, and we'll see you on the other side of this webinar sneak peek.
And this one I thought was kind of interesting. It caught me at first glance here. There's almost like here taking the same circle and inverting it to try to see if that would help at all. So that one's really interesting as well. Like, all of these are super interesting approaches to trying to solve this. Yeah, here's one here. This one, I saw this come in 2 different times, like putting a square inside the circle, I thought was pretty cool. I'm wondering, I think I know who it was. Does that individual want to share like your thinking here? Now, I also want to make sure that we don't assume we know a formula. So I'm curious if how we might be able to break this down if we didn't know a formula. Is there a logic here that we might be able to lean on at all? maybe challenge everyone to think about something. And this would be where what I might ask students to do next. So they've come up with all these ideas. We reshare these estimates, which is fantastic. And then I might ask them, like, a lot of people defaulted to squares, right? In some way, shape, or form. And even, we saw, like, even here, like a square inside the circle. It's like we're fascinated by this idea of squares and rectangles. And to me, it's like, wait a second. Like, I wonder if there would be another way that we might be able to create a square out of this. I'm going to put it to everyone else. Like, is there anything else that we could do? And like, I've got myself a brand new circle that I'm going to try to like model whatever you share. I might even cut another one just in case other people have other ideas as well. But I'm really curious about this. Like, what might we do to like take this area of the circle and like make it more like something that we know how to handle? Because I don't know about you, but circles are kind of hard. Yeah, we'll definitely do that. Like, I'm curious, is there anyone out there in the chat, or turn your mic on? Like, are you feeling Jon on this strategy? Like, are you seeing the logic? Because like, I'm looking at it too, Jon. Like, I could think about it. It's like, it seems like the wider the base of your triangle, the more imprecise you'll become, right? Because like that, like you can kind of see it where, there's that sliver. That gets bigger and bigger. So if I did like only 4 triangles, then I'm in trouble. That's kind of what, we kind of ran into the same problem with. What a cool approach, because Jon, like the way you've done it, you did it through this logic of triangles. And then the way I was thinking of it, which is different. But again, like this is the beauty of it, is it's all perspective and it's all kind of what comes to mind for you. I know for me, and I'm going to throw the document camera on here. Like for me, when I looked at this, so like Jon, his little chunks basically are 13 tile chunks basically, and then you said you had like 164 of these chunks in total. Something that's also cool is like, imagine on the other side, Jon, I thought of this as you were talking, but I was picturing like there's going to be like a mirror image, right? Well, this is not the same size as that, but you know what I'm saying. And it's like, well, if this is 13, then it's kind of like I could like take this and I could say, well, like I only need half of them, and they're 26 tiles. So that's like another way we maybe cut down on the multiplication. Now, what students might do, like if we think back to this continuum idea, everybody wants to go to like a shape that they know. Like everybody feels good about squares. They feel good about rectangles. Jon felt good about triangles. But remember, a triangle is simply taking a rectangle and cutting it in half, right? Like if I cut this in half, I get 2 triangles, right? So it's like there's your half times length times width right there, right? Like that's where your formula for triangles comes in. I'm not going to dare try to fold this correctly because that's going to be really hard. But if I do, you'll see it. Like look at that. I've got the same. Oh, it's kind of too bright. Oh well. Oh, there it is. You can see it. Nope, not anymore. Anyway, you get the same triangle on both sides. So it's like the area of a triangle formula is the area of a rectangle formula. We're just going to half it. Okay, so now I'm like, well, Jon's saying I can use triangles to do this. I wonder if I could take like a circle, and I wonder if like there's something I can do to like make my life easier. And actually there is, like a student could take this and go, you know what, like it's not going to be perfect, but if I go at, like I got semicircles, and I don't know how to do the area of that, but if I do this and I go, well, let's see here. If I go and I do this, it's like you can kind of see Jon's idea emerging here, except the only difference that I'm going to play with is I'm going to go like this, and I'm going to go, well, wait a second. Let me just keep cutting these. Yeah, like I was picturing it kind of like, you know, pieces of pizza, but like now I'm seeing your triangles through your explanation, which is pretty cool. And it's like, as we do this smaller and smaller, like the cool part is white paper is not going to be super helpful for this, but I'm going to do it this way. Like if I take all these triangles and I start to break them down, and it's like, okay, well, these ones were across from each other. If I do this, oh my gosh, like look what starts to form. Now, I'm hoping you can see, like if I get these to the size Jon was talking about, Jon was like, you know what? Let's make these even smaller. Holy smokes. And when I do this, and I'm cutting that out because I want to make sure everybody realizes in the classroom, we want students to be experiencing this, right? We want them to actually create it. But if I was to take this same circle here, and again, we take this idea and we're like, okay, well, like, let's make Jon's triangles. There we go. That's not that helpful. But like, watch what happens when we do this a little bit more. We're like, all right, how about now? We're getting somewhere, right? I don't know if you can still see this though, like keeping in mind, like here's our circumference around the outside. Yeah, it's too rounded to be accurate. Okay, let's keep cutting these. Check it out. Oh, we're getting pretty close. What if let's keep going. Oh, okay. So you're telling me like that's not good. This is better. This is better. And this would be bestest, right? So if I could even like, we can outdo Jon's scenario if we could even go less than a tile and make it like super flat. Like this is like calculus, right, Jon? Like this idea of limits and like, you know, approaching infinity and all this. It's like, if I zoom in, I'd still see some roundedness there on the outer edges. So here's what I want everybody to think about, okay? Because like we know a lot about this this particular circle, right? We know that it's 52 tiles across, right? Jon, you had confirmed or reiterated for us that it's like 164-ish tiles all the way around, right? Like we saw that there. There's the 164. If we just wrap it around the tile, it'll look, a little bit more. There we go. It took a while, but there it is. So you could see those 164. My question to you then is the following. What are the dimensions then of this rectangle? And I want you to think about that again, okay? So I'll give you this look. I want you to think, I got 52 is the diameter all the way across the circle. I got 164 all the way around. Where does that help me with trying to find the dimensions of that rectangle right there? Because remember, like I'm literally cutting this thing out, right? Like I'm literally trying my best to cut this thing out and make this into a rectangle. It's just not as precise yet over here. So I want you to think about that. I wonder if we could do this like and pretend like we did it, but not actually have to do it, right? Like that's kind of like what math does for us. It's like, well, you don't even have to cut it. I trust that if I cut it, here's what's going to happen. I wonder, can anybody help us with that? What's that going to look like, sound like? Yeah, that's super cool. So you were saying like it's half of this. I'm wondering, can like Anne-Marie, like, can you help us? Like, why half and not just like 164 here? Like, Yeah, and like check out, I don't know if I changed, yeah, you can see it. Check out these pieces. Like I'm going to keep everything where it was, but I'm just going to rearrange the pieces, but keep the tiles where they were. So you can see the colored tiles around or the circumference. And look what happens when we rearrange these pieces. Half of them are on the top, half of them are on the bottom. And then what about the sides? Like what are the dimensions of the sides going to be? Like what are those going to be? Wondering, anybody out there? It's going to be the radius, right? Not the diameter. Because again, we've taken these pieces and like Jon did one piece. It's like here we're taking the piece and we're like, gluing it to another piece. So we're only making it to the center of the circle. So holy smokes, we have an area formula here that we've decided. Like we know that that's going to be the circumference. Like we know that. So it's like, it's 164 tiles, but it's shared equally amongst the two sides. So that would be like, we're going to use partitive division. We're going to like chop it in half into two parts, and we're going to give half, one part this much and the other part that much. So you've got that taken care of. And then the sides, we're going to just use the radius. Now, my wonder is like, can anybody help us with like, what can we do to try to like make this into a formula? Like, I know we're coming out with the numbers here, and I'm feeling pretty confident about that we're going to come out with a pretty close, precise number of tiles, but I'm wondering, like, how can we generalize this? Like, what is it that we're actually saying? What are we doing here? Like, how can I put this into words so somebody else would be like, oh, I can repeat this process? Ooh, and I'm guessing because like we know the circumference is used on two of the sides, right? That makes sense. Totally. All right, so let's do that. So I think we're all in agreement that, again, we're going to take the circumference, we're going to split it in half. It's going to give us 82 tiles on each side. So we have the numeric value. What is the circumference again, based on our exploration around the circle from episode 1 and then today continuing that? What did we do again to find the circumference? Awesome. So we took 3 and some, right? 3 and some. I think it was like 3 and yes, so 14 hundredths. That was like our approximation, right, of that relationship. It's a never-ending, non-terminating decimal. Just keep going. But we kind of truncate it down to that point. Awesome stuff. So I could say it's like, basically the circumference is like this 3 and 14 hundredths, or this thing we call pi. And we multiply it by the diameter. But in this case, so I'm just going to rewrite that. In this case, like our side lengths are half of that. So is everybody cool with that? Like we see it's like half of the circumference on both sides. Like that's going to be our length here. Now I'm wondering, does anybody know, like, can somebody tell me what is half? Like, can we do this a little better? Like I see half of this number. I wonder if there's a way that we can clean that up a little bit. Like in other words, what are we doing there? Yeah, what do you think? I love it. Check this out. Half of the diameter is the radius. So now I've got basically, holy smokes, I've got this 3 and 14 hundredths times the radius, because we're like, why do diameter divided by 2? Like that just feels like a lot of work. We know the radius is half the diameter. So let's put that there. And we know that answer here is 82. Like we already know that, but we're trying to generalize. And you folks told me that the diameter was split in half on either end. So it's like we've got essentially, I just heard you say like it's half the diameter. So that's another radius, right? So now my wonder is like, what can we do with this in order to figure out the area? I've got this big rectangle. I know that my dimensions are essentially, the width is the radius. The length is pi times the radius. What are we thinking here, friends? Pi r times r is the same as pi times a square with the dimensions of r, which is pretty awesome. Like if I actually kind of look at this in particular here, we can actually see the pi-ness of these numbers of squares. Because like, I don't know about you, I knew this formula was pi r squared. Now, mind you, a lot of people confuse them, or like that's either perimeter or it's area. Like, there's always this confusion. But right now it's like we're helping to see that it's like, no, there is no confusion, because look at this. If I go 26 tiles by 26 tiles, and guess what? I got another one of those squares right here. There's like a second one there. And then we've got a third r squared. So you can actually like see these squares being formed. And then don't forget about that little extra at the end. Again, that 14 hundredths of a radius, which is in this case going to be about 4 tiles or so. So the whole purpose here is, again, kind of thinking about this continuum for measurement and trying to essentially bump into how the area of a circle actually works. So we can actually see it here. And by golly, if we go ahead and actually count up all these tiles, my friends, I'm wondering, did anybody update their estimates, update their precision on their estimates? What are we ranging from here? Like, what are people feeling now? So if you work this out and you go, holy smokes, like that's a lot of tiles. We're looking at like 2,100 and what would it be? 32 square tiles. Holy smokes. That is a lot of square tiles. Now, the crazy part is, again, Jon and I have said it so many times, we both went to school for mathematics, and I never, like into post-secondary for mathematics, and I never understood why this formula existed, how it existed, or how it worked. And I'm hoping that you're seeing that here. Even if you're a PJ teacher, I'm hoping you're seeing the importance of the conceptual, regardless of the age range that we're working at. It really, truly is so important for students to see that.
Hey, Math Moment Makers. So you had a chance to dive in and have a look inside that webinar with some educators and try to emerge this idea of the area of a circle. I'm curious, how do you introduce the area of a circle formula for students? How do you emerge it in your classroom? We'd love to hear it in the comments below. Again, make sure you hit that like and subscribe button. And also, if it's on YouTube, go ahead and hit that notification bell. It does a huge service to other educators by letting YouTube know that this was a valuable information or a valuable video for yourself. Now, keep in mind, you might be wondering, where can I actually find this task? Like, can I utilize it myself? And the answer is yes. You can head to my, I'm going to call it my older website. It's the blog I used to blog at before we began Make Math Moments at tapintoteenminds.com. You could Google it, just type it into Google. You can even just type in tile circle math in Google, and this task will emerge, and you can access both the circumference portion of this task as well as the area portion of this task. And also keep in mind that we have all of our latest problem-based lessons and units of study, including very soon we're going to have Tile Circle, a full unit dedicated to emerging pi, exploring the circumference, and getting into the area and emerging area. And keep in mind that with each one of our problem-based units, not only can you access them openly and freely, but inside, if you decide to become an Academy member, you can join and you can download our PDF handouts for the purposeful practice that go along with these units, and also access all of the slide decks and resources so that you can have them handy on your computer and not necessarily have to rely on streaming or any of those issues. So definitely check that out. As an Academy member, you can join free for 30 days and you can cancel at any time as well. So we encourage you to get in there, at least have a look around, and then also explore some of the other courses and other resources that we have available to you as a math moment maker. Well, until next time, my friends, I'm Kyle Pierce. I'm from MakeMathMoments.com, and I want to thank you so much again for hanging out with us. Do me a favor, leave a comment below and let us know what was something that resonated with you here. Do you have a suggestion for us, something that we should check out? Let us know in the comments. It's so helpful to hear your responses and your reflections. All right, we'll see you in the next one. Take care.